We are moving into the fifth model. Let me recall. First model we discussed the basics of probability, and the second model we discussed the random variable. The third model we discussed the moments and inequalities, and the fourth model we discussed the standard distributions, both the discrete and continuous type. Now we move into the fifth model, that is random vectors. In most of the random experiment, you may have a omega in which you may able to create many random variables simultaneously, and also sometimes the interest will be finding the sum measures together, or given one set of measures takes this value, what could be the distribution of other random variable, or sometimes you may interested to find the distribution of more than one random variable at the same time. So till now we have discussed only one random variable, then later we have discussed a function of a random variable, that means again it's another one random variable. There is a possibility you may need to study more than one random variables at the same time or simultaneously or together. In that case, you need a random vector. When we use the word random vector, that means it is a n-dimensional random variable. That means we put n random variables together, that we call it as a n-dimensional random variables or random vector of size n. That means each one is a random variable and we are studying n random variables together or jointly. Many real world problem you may need to study the distributions of more than one random variable jointly. Therefore, we need a random vector. That means whatever we have understood the concept of random variable and their distributions and movements, the same concept has to be extended from one dimensional to multidimensional. So whatever the calculus we have used, calculus means finding the integration or finding the derivative and so on, whatever we have done the calculus part with the one dimensional variable or one variable, now we have a n-dimensional random variable, so the corresponding calculus of several variable has to be used. Let me explain how the random vector come into the picture. The omega consists of many samples. It could be finite or countably infinite or uncountably many. The random variable, one random variable is defined as x1. Another random variable defined from the omega, that is x2. Like that, there are many more random variables defined in the omega, that is a real valued function from omega to r satisfying the condition, that is x inverse of minus infinity to small x semi closed interval belonging to f, then only the real valued function is a random variable. That means you have a probability space omega f p. Omega is a collection of all possible outcomes and f is the sigma field on omega, and p is the set function satisfying the three conditions, the Kolmogorov axiomatic conditions. Therefore, p is a probability. So this is a probability space. In this probability space, x1 is defined, the same probability space x2 is defined. Like that, many more random variables are defined in the same omega. Now we are going to create a random vector by making a few random variables together or jointly. That means if you go for x1 comma x2 together, then this is called a two-dimensional random variables, or it's a random vector of size 2, x1 and x2. That means the same omega x1 comma x2 is defined such that the possible values is going to be in the two-dimensional plane. This is x1 and this is x2. Earlier the x1 is defined from omega to r. Now the x1 comma x2 is defined from omega to r cross r. So again, each one, x1 is a random variable, x2 is a random variable. Together we call it as a random vector of size 2 or two-dimensional random variable. The same way one can define n-dimensional random variable x1, x2 and so on till xn. Each one is a random variable, therefore this is a n-dimensional random variable. In short, RVS, random variables. That means we can go for finding what is the joint distribution of n-dimensional random variable x1 comma x2 so on xn. Earlier we used the word distribution of x1. Now we are studying the distribution of n random variable together or jointly. Therefore it's called a joint distribution of n-dimensional random variables. So first we can discuss what is the CDF, cumulative distribution function. If it is a discrete type random variable, one can discuss what is a joint probability mass function. If each random variable is of the continuous type, then one can study what is a joint probability density function of n-dimensional random variable. Initially we study all the random variables of the discrete type or all the random variables are of the continuous type. Later we will see one random variable of the discrete type and the other one is of the continuous type and so on. That we will do it in the later. So our interest is to find the joint distribution of n-dimensional random variables in which each one is a random variable. That means that satisfies the definition of random variable. Therefore this is a n-dimensional random variable. First let us go for how to give the definition of a joint CDF. Joint CDF of, instead of going for the n-dimensional random variable, first we will restrict to the two-dimensional random variable. Once we discuss the two-dimensional random variable CDF, then it is easy to visualize or easy to understand for more than two-dimensional random variable. Okay, it is x1 comma x2. The joint CDF can be written as the two functions x1 comma x2 is nothing but the probability of capital X1 is less than or equal to small x1, capital X2 is less than or equal to small x2. Both x1 and x2 lies between minus infinity to infinity. Similar way we have defined the CDF of a one-dimensional random variable. Now we are defining the CDF of two-dimensional random variable with the two variables small x1 comma small x2. That is nothing but a probability of capital X1 is less than or equal to small x1 and capital X2 is less than or equal to small x2. That is nothing but P of collection of W such that under the operation x1 the w has to be less than or equal to x1. That means this value can lies between minus infinity to small x1. Also the same w under the operation x2, it gives a value small x2, and the w's belonging to omega. That means we are collecting a few possible outcomes satisfying the condition under the operation x1, it should give the value less than or equal to x1. Under the operation of x2, it gives the values less than or equal to small x2. So we are collecting those possible outcomes, then finding the probability, and that probability of this possible outcome satisfying this condition, that is going to be the CDF at the point x1 comma x2, where small x1 can lie between minus infinity to infinity, small x2 also lies between minus infinity to plus infinity. The collection of w such that this condition, we can label this as the a suffix x1 comma x2. This is an event, because whenever you collect a few possible outcomes, that is nothing but the event. So the event a suffix x1 comma x2, that is a event. That means the probability of event, by using a Kolmogorov axiomatic definition, probability of any event or p of any event always greater than or equal to 0, and p of omega is equal to 1, and p of union of ai's, that is equal to summation of p of ai's as long as ai's are mutually disjoint events. With the same logic, the p of any event getting from the different values of small x1 and x2, this is also going to satisfy the Kolmogorov axiomatic definition. Therefore, one can make what are all the conditions or what are all the properties is going to be satisfied by this capital F. So let me write down. It satisfies the first condition, the capital F of x1 comma x2, that is non-decreasing and continuous from the right, that means it is a right continuous, with respect to each coordinate that is x1 x2. It is a non-decreasing as well as a continuous from right with respect to each coordinate. That's the first point. Second point, the limit of x1 tends to plus infinity, x2 tends to plus infinity, the CDF x1 comma x2, limit x1 tends to plus infinity, x2 tends to plus infinity, f of x1 comma x2 is always 1, and the limit x2 tends to minus infinity of f of x1 comma x2, that is equal to 0, and the limit x1 tends to minus infinity f of x1 comma x2, that is also 0. When both becomes a positive infinity, it becomes 1. When either one of them is minus infinity, the limit x2 tends to minus infinity or limit x1 tends to minus infinity, that function of x1 comma x2, that is going to be 0. The third point, for every a comma c and b comma d with a is lesser than b and c is lesser than d, we have, I can just draw the diagram first, then I can go for it. That is easy. So I can take a small box in which this is going to be A and this is going to be B, and this is going to be C and this is going to be D. Correct? I can go for, after drawing the diagram, now I can go for f of b comma d minus f of b comma c minus f of a comma d plus f of a comma c, which is greater than or equal to 0. So the cross is going to have a positive symbol and the tick mark as a negative symbol. That means f evaluated at b comma d minus f evaluated at a comma d and b comma c with the minus sign, then plus f evaluated at a comma c, that value has to be greater than or equal to 0. Whenever you have a two-dimensional random variable whose CDF always satisfies these three conditions. The third condition is a very important condition, in the sense, even you may have a real valued function with the two variables, satisfying these two conditions may not be a CDF of a two-dimensional random variable unless otherwise it satisfies the third condition. But if you have a two-dimensional random variable, you will have always a unique CDF with the two variables that satisfies all these three conditions. CDF of two-dimensional random variable can be represented in the form of graphical. So one can visualize the CDF in the form of x-axis, x1, x2, and this is going to be CDF of x1 comma x2. So this is possible only for two dimensional. X1 is one random variable, x2 is another random variable. So z axis, that is a CDF of x1 comma x2. Whereas you cannot visualize, you cannot make a graphical representation of more than two-dimensional random variable. Let's go for one simple example in which we can conclude whether this is going to be a CDF or not. As an example, let x1, x2 be a two-dimensional random variables with CDF x1 comma x2, that is either 0 when x1 is less than 0 or x1 plus x2 is lesser than 1 or x2 is lesser than 0. It takes a value 1 otherwise. Verify whether the capital F is going to be the CDF of a two-dimensional random variable. That means this is a real valued function with the two variables. Whether this satisfies the three properties which we have given. If all these three properties are satisfied, then you can conclude this will be the CDF of a two-dimensional random variable. You can easily verify the first two properties. The function is a non-decreasing as well as continuous from the right. Similarly, you can easily verify the limit of x1 tends to plus infinity, x2 tends to plus infinity, that value is 1. either x1 is minus infinity or x2 is minus infinity, the limit is going to be 0. That also can be easily verified. We have to verify the third condition, that is the for any 2 points, the CDF of the difference at 2 points with a positive sign, 2 points with a negative sign has to be greater than or equal to 0. For example, you do it with the probability of x lies between x1 lies between 1/3 to 1, comma x2 is lies between 1/3 to 1. If you compute this probability, that is nothing but f at the point 1 comma 1 minus f at the point 1 comma 1/3. I am using the same property, minus f 1/3 comma 1 plus f 1/3 comma 1/3. If you substitute the value f of 1 comma 1, that is 1, f of 1 comma 1/3, that is again 1, f of 1/3 comma 1, again 1, f of 1/3 comma 1/3, that is 0, and this value is going to be minus 1, which is not greater than or equal to 0. So, for any arbitrary points, this third property has to be satisfied. So, since the third property is not satisfied, you can conclude this f is not a CDF of the random vector x1 comma x2 or the 2-dimensional random variables x1 comma x2. We will give some example in which that is going to be CDF. So, example 2. Let x1 comma x2 be a 2-dimensional random variables with the function f of x1 comma x2 is 1 minus e power minus lambda x1 minus e power minus mu times x2 plus e power minus lambda x1 minus mu x2. So, this is going to be the value when both x1 and x2 lies between 0 to infinity, otherwise it is 0. We can verify whether this is going to be the CDF of 2-dimensional random variable. By seeing the function, you can easily say when x1 and x2 is positive infinity, it becomes 1. Either x1 or x2 is going to be minus infinity, that is going to be 0, and it is a non-decreasing function and continuous from the right. Therefore, the properties 1 and 2 are easily satisfied. For different values, one can able to verify the third property also will be satisfied. Therefore, one can conclude this is going to be the CDF of a 2-dimensional random variable. So, I am not giving the proof of the third property, but that can be verified. We can conclude this is going to be the CDF of a 2-dimensional random variable. Suppose we know the CDF of x1 comma x2, one can able to find the the CDF of any one random variable. That is, one can find the CDF of random variable x1 as a function of small x1. That is nothing but the probability of x1 less than or equal to small x1. That is same as probability of x1 less than or equal to small x1, which intersect all the union of x2 less than or equal to small x2 for all possible values of x2. That is same as the probability of union of all possible values of small x2. x1 is less than or equal to x1 and x2 is less than or equal to small x2. That is same as the P of union is nothing but limit x2 tends to infinity, P of x1 less than or equal to small x1, capital X2 less than or equal to small x2. That is same as limit x2 tends to infinity, capital F of x1 with x2. That means if you know the CDF of x1 comma x2 by taking limit of the other variable tends to plus infinity, that will give the CDF of the other random variable. Similarly, the CDF of the random variable x2 as a function of small x2, that is nothing but limit x1 tends to plus infinity of CDF evaluated at the point x1 comma x2. So this is valid for a two-dimensional random variable. So this concept can be extended to n-dimensional random variable. That means suppose I denote capital X as a n-dimensional random vector. Instead of again and again writing an n-dimensional random variable, I can write capital X with the CDF capital F. That means F also has n variables. Then we can find the CDF of any one random variable. Suppose I want jth random variable. Suppose I want to find out the CDF of jth random variable. That is nothing but limit x1 tends to infinity, limit x2 tends to infinity. I assume that j is in between 1 to n. Therefore, limit x j minus 1 tends to infinity, limit x j plus 1 tends to infinity, and so on, limit x n tends to infinity of capital F, which has the elements, just I will write down in the next line, x1 comma x2 xn. So this is a way one can get the CDF of a one-dimensional random variable from the CDF of n-dimensional random variable, where j can be 1, 2 and so on till n. In this exercise, I have not said whether the random variable is of the discrete type or continuous type or mixed type. So based on the each random variable or of the discrete, continuous or mixed, one can discuss the joint probability mass function or joint probability density function and so on. So at present we don't know what is the type of each random variable, therefore we stopped it at the CDF of the n-dimensional random variable. Once we know the type of each random variable, then one can go for studying the probability mass function jointly, probability density function jointly. That is going to be the second lecture.